Welcome. In this session, I'll outline a method that we will use to solve nonlinear inequalities algebraically. This method works for all elementary functions, even though we are going to talk only about rational functions for now. This works for any function that's continuous except at a finite number of values, including exponential and logarithmic functions and functions built from them. This is based on the fact that if you have a continuous non-zero function in an interval, then it cannot change its sign. So given a function, we try to find such intervals and then determine the sign in each interval by using test values. As I said, we'll illustrate this mostly by using rational functions. So first step, which is just algebra, is to bring all the terms to the left, write it in the form something is compared to 0. In this example, we have a rational function greater than or equal to 0. Then we identify the points where this function is 0 and where it's discontinuous. For rational functions, this just amounts to where the numerator is 0 and where the denominator is 0. So to do this, we will factor the numerator and the denominator. We see the numerator is 0 when x is 4 or negative 1, and the denominator is 0 at 2 and negative 3, so those are the discontinuities. So if I take intervals which do not contain any of these four numbers, then the function has the same sign throughout that interval. So we need to first find those intervals. So we'll plot these points and imagine cutting the real line at these numbers, and those will give me the intervals. So I have the interval from negative infinity to negative 3, negative 3 to negative 1, negative 1 to 2, 2 to 4, and 4 to infinity. So just arrange the zeros and discontinuities in sequence and then take the interval starting at negative infinity going to infinity. If we have radicals or logarithms, so that the domain doesn't contain most real numbers but starts and ends at some finite values, we have to start and end at the appropriate numbers. For rational functions, it will start at negative infinity and at infinity. Then we determine the sign at each interval. We can do this in a couple of different ways. I prefer to use a combination of the two methods, which is that we take a test value in each interval and then use the factorization to determine what sign it should have. So the first interval is negative infinity to negative 3. Let me pick negative 5 in that interval. If I plug in negative 5 into the factored form of the function, I see that I have the numerator negative times negative. In the denominator also negative times negative. So the whole fraction will be positive. In the interval from negative 3 to negative 1, I will pick negative 2. If I plug that in, the numerator I have negative times negative. The denominator I have negative times positive. Negative 2 plus 3 is positive. So it's positive over negative or negative. Or I can simply say there are three negatives, odd number of negatives make a negative. At 0, if I plug that in, I get negative times positive over negative times positive. Two negatives, so the end result is positive. And then between 2 and 4, I can pick 3, where I get negative times positive over positive times positive, so that's negative. Finally, for the interval 4 to infinity, I will pick 5. Then I get positive for each factor, so the whole fraction is positive. Now the original question was, where is this function greater than or equal to 0? Greater than 0 means positive. That's the first, third, and fifth intervals. What about 0? We already know that that's 4 and negative 1. So we combine the two things, take those intervals and include the points negative 1 and 4. So I'm going to do that by changing the parentheses to square brackets, which is an indication those numbers are included. And those are the intervals where this function is greater than or equal to 0. This illustrates how we solve nonlinear inequalities algebraically. I will stop here. Goodbye for now.